Welcome to ATMOS 5000, day number 32. We're focusing in on the Stull textbook, Chapter 8, Section 8.3. We're going to introduce radar today. We're going to talk about the fundamentals of radar. We're going to introduce the radar equation. We're going to learn how to estimate rainfall rates from the return signal from radar, and we'll learn about the difference between precipitation radar and Doppler radar. And then we'll look at an example of using the Doppler effect to determine the wind profile of the atmosphere remotely. So what is radar? Radar is an acronym which is basically describing radio detection and ranging. That's where the letters actually come from. It was developed during World War II for the detection of enemy aircraft, but it's also useful in identifying the location and intensity of precipitation. And the basic idea is that you have a transmitter/receiver that will send out a beam of electromagnetic radiation, which travels at the speed of light, and it will, in the absence of anything in the atmosphere that will scatter, there won't be any backscatter, and you'll get no return signal. But if you do have targets in the atmosphere, each of those targets will transmit or scatter a very small fraction of the transmitted energy in the backward direction that can then be picked up by the transmitter. And by tracking the length of time between when the pulse is transmitted and when the backscatter returns, you can get an estimate for the distance of that target away from the radar. And the information about the size of the targets is also contained in the backscatter information as well, as larger targets will return a larger proportion of the transmitted energy back to the receiver. So here we have a weather radar that's in the dome, which is sending out a signal, and it is impacting a thunderstorm. And you can see that it's actually not interacting with the white portion of the cloud, which are the cloud droplets, and that's because the wavelength was actually chosen in such a way that the return signal from the cloud droplets is too small to measure. And instead, this radar is focusing in on returning backscattered radiation off of the rain droplets that are formed inside this cloud, and each of those individual rain droplets will transmit part of that radiation back to the receiver. And so, typically speaking, only a very small amount of the transmitted energy is scattered back towards the radar, and we typically need fairly large dishes to concentrate that energy to make it measurable. So, one of the things that helps focus the radar beam is to have a very small beam width, and the beam width is controlled by the particulars of the radar itself. So the beam width, delta beta in this case, is equal to A times the wavelength over the diameter of the beam spread. And for the National Weather Service radars, this constant A is 71.6 degrees. For many weather radars, the beam width is less than 1 degree, so that you'll get a very focused beam. And at close range, that area of that beam is pretty small. It's 0.1 kilometers, probably. And as the range increases, the beam will spread out, and you'll end up with much larger sample volumes that are being sampled as you move further away from the transmitter. The radar range is easily calculated by measuring the round-trip time for the pulse to get from the transmission to the target and back. So the range is equal to the speed of light times the time divided by 2. And the maximum unambiguous range of the radar system is controlled by the pulse rate frequency. Here we have the maximum unambiguous range, R max, is equal to the speed of light divided by 2 times the pulse frequency. So if you want to increase the range of your radar, then you not need to send out pulses not quite as frequently. There are several different methods that we use to scan the atmosphere. One of those is what we refer to as the plan position indicator, the PPI. And here we have the radar. That beam is put out at a particular elevation angle and then is spun 360 degrees in the azimuth so that you get full coverage of the sky. This radar beam has an angle that is above the horizon, so it will be sampling different altitudes as you move further away from the radar transmitter receiver. By basically altering the elevation angle of the radar and keeping track of the information, it's actually possible to use the information from the multiple scans to create a constant altitude plan position indicator, a CAPPI, and so it would give the precipitation at one altitude over the entire range of the radar. It's not something that is a product that's typically made available to the public, but it is available inside the confines of the radar operators. Another way that you can operate the radar is to keep it focusing in at one azimuth angle and vary the elevation angle so that you're looking through a cross-section, a vertical cross-section through one part of a storm. This is referred to as a range height indicator, RHI, and that can actually help you probe for where the precipitation is at in the cloud and where hail might be in the cloud as well, along with the freezing level as well by looking at the location of the bright band. If you have control of the radar, you can actually do an arbitrary vertical cross-section as well, which can give you detailed information about the structure of an individual storm that you happen to be looking at. The National Weather Service WSR-88D radars actually scan surfaces at different elevation angles, and these elevation angles range from the National Weather Service radars for 0.5 degrees to 19.5 degrees. And so they will do a scan at 0.5 and then they'll ramp it up to a different elevation angle and then spin it around 360 and then a new elevation angle and spin it around 360. And it takes about 5 minutes to do a complete scan between 0.5 and 19.5 degrees. So this is the network of the National Weather Service radars. There is pretty good coverage in the eastern half of the United States. The coverage in the west is fewer and far between. And there still are places like central Utah and the Four Corners area and conveniently Area 51 in Nevada where there is not radar coverage, as well as in Oregon and Montana, Wyoming. There's some areas as well. But these radar systems were funded by Congress because of their ability to predict tornadoes, and that's a much bigger issue in the eastern half of the United States, and that kind of explains the higher density of radar systems in the eastern half of the United States. So those elevation angles, as mentioned before, range between 0.5 and 19.5 degrees. The reason they don't go below 0.5 degrees is because they want to try to minimize ground clutter. And of course, the beam gains altitude as it travels away from the radar. And as it turns out, most people don't realize this, but the radar can't see directly overhead. And we refer to this as the cone of silence. And it appears as a ring of minimal or non-returns around the radar. And the other thing to note, of course, is that the sample volume will increase as the beam travels away from the radar, so that the resolution is degraded as you move further and further away from the radar. So this figure shows the effect of the elevation angle on the sample volume for the National Weather Service radars. So for the 0.5 degree elevation angle, the height of the beam stays relatively low in the atmosphere, and by the time you reach 120 miles away from the radar, that 0.5 degree is ranging between about 10 to 20,000 feet. You can contrast that with, say, the 4.3 degree elevation angle. By the time you reach 120 miles away from the radar, the 4.3 degree elevation angle is located between 60 and 70,000 feet, which is going to be above most of the storms, because that's going to be up in the stratosphere. And so you can see that these higher elevation angles will give you information about the vertical variation of precipitation, but the higher elevation angles are primarily going to give you information close into the radar itself, because before long they will be too high to provide information about the storms. So here we have a graphical example of the planned position indicator radar scan. So we have the radar, which is located in the middle, and it's going to spin around. And as it spins around, this is the coverage that you would get from that radar. Of course, you have that cone of silence in the middle, immediately above the radar, and at elevations all the way down to zenith angle from 0 to 19.5 degrees will give you a cone of silence. The other thing that we need to know about the radar beam is how it will propagate. So in a vacuum, the radar pulses would propagate at the speed of light in a straight line. But the beam is not passing through a vacuum. It's passing through an atmosphere that has variations in density, and those variations in density are caused by pressure variations, by temperature variations, and by humidity variations. And as it turns out, because the density of the atmosphere decreases with height, it causes the radar beam to be refracted down towards the more dense air. And the amount of that refraction depends upon the vertical density gradient. So if you happen to have a really strong vertical density gradient, you can refract that radar beam all the way down to the surface and it will hit the ground. That would be essentially an example of ducting or trapping, depending upon whether or not the surface is reflective or whether or not the surface is rough. If the surface is rough, then the radar beam will not reflect off the surface, and you'll just get a strong signal at that distance, at that range, and then nothing beyond it. And in that's the example there is part C of the figure. The ducting is where the surface is reflective and the radar beam keeps impacting the surface before bouncing back up into the atmosphere and then being refracted back down. And you would have, of course, a very strong return signal at each point where the radar beam hits the ground. So we like to think that the radar beam does the standard propagation, which is shown in A, but there are some atmospheric conditions when you can have anomalous propagation that would obviously impact the ability of the radar to do its job, but would also potentially lead to erroneous interpretations if you don't understand what's actually going on with the radar beam itself. So the beam propagation equation, Z is the height above the surface of the radar beam, is going to be equal to the height of the radar transmitter minus the effective radius of curvature of the Earth, RC. And we're going to take that RC to be 4/3 times the radius of the Earth. And that is assuming that we have normal atmospheric conditions and we don't have anomalous refraction in the Earth's atmosphere. And then we are being multiplied by R squared, which is the range of the radar, or the radar range. RC, of course, is the effective radius of the curvature of the Earth again. And then we have the sine of the elevation angle, and all of that's inside the square root. So this beam propagation equation will give you an idea of what elevation that beam is at a certain range away from the radar, assuming standard atmospheric conditions and normal propagation. The radar equation, which was basically discovered during World War II, was the result of a massive scientific effort on par with the Manhattan Project. If you understand military history, you'll understand that the ability to see and detect enemy aircraft at a distance has a huge strategic value. And so the United States poured lots and lots of money into trying to be able to develop radar systems that could do just that. The benefactor of that was actually atmospheric sciences, because we were able to come up with this radar equation that would work for aircraft, but it also is applicable to rain droplets in the atmosphere as well. And the radar equation looks at the relative power received, so PR is the power received divided by the power transmitted, PT, is equal to this constant B, which depends upon the type of radar that you're using and the power of the radar that you're using and the beam width of the radar that you're using and the gain of the radar that you're using. So we will lump all of those into the equipment effects. And then we have the atmospheric effects, where we have the K value, which is the refractive index of the atmosphere, divided by a constant LA, which we'll talk about here shortly. And then that whole quantity squared, and then times the range inverse squared. So this is basically looking at how the beam spreads out from the individual scatterers. And we have a constant R1 divided by the radar range. So basically the return signal that we're going to get is going to be proportional to 1 over R squared. And then we have the target reflectivity, Z, and that's over a constant Z1. So Z is essentially the reflectivity of the target. The larger the target, the bigger the target reflectivity. And so that is very useful at determining the size of the rain droplets. So that K, that index of refraction, is essentially a dimensionless constant. And the liquid droplets are more effective at scattering microwaves than ice crystals. So we use a K value or K squared value of about 0.93 for liquid droplets and about 0.21 for ice. And then the radar range in kilometers is that returned energy that we get. And because of the 1 over R squared, the energy that we receive from distant targets is much weaker than from closer targets. And then we have that Z, which is our target reflectivity factor. And if we are assuming that we're looking at droplets in the atmosphere, the things that will increase the reflectivity or increase the reflectivity factor of an individual volume is having a larger number of droplets, or having droplets that are big in a given volume of the air. Because what we're looking at, the reflectivity factor, is the sum of d to the 6th power summed over all of the individual droplets divided by the volume over which this beam is impacting. And so you can have multiple different size droplets that will contribute to that. So you really need to know information about the droplet size distribution, which luckily Marshall and Palmer figured out for us for liquid rain droplets before. This all gets much more complicated and fuzzy when we're dealing with hydrometeors that have an ice component to them. So we can look at the radar equation, and we can do this in the log form, which is more useful for us. So we have dBz, which is essentially the return signal, the reflectivity factor Z, on a log decibel, on a decibel scale. So dBz is going to be equal 10 raised to the power of all of this stuff in between. So we have the log of PR over T plus 2 times the log base 10 of the range over this constant R1 minus 2 times the log base 10 of the index of refraction over that quantity LA minus the log of B, where B is the equipment factor. So R1 is a range factor, which is going to be the square root of Z1 times the speed of light times the pulse duration, delta t, over the wavelength squared. And for the National Weather Service radar, for the conditions for that, we get an R1 about 2.17 times 10 to the minus 10th kilometers. The quantity LA is a dimensionless atmospheric attenuation factor, which accounts for the absorption and scattering of the microwave pulse as it travels through the atmosphere. A LA of 1 means that there's no attenuation, and if there's more attenuation, then this quantity will be greater than 1. And B, of course, is the information that is contained about the equipment factor. So it includes information about the gain, capital G, about the beam width, delta beta, and for the National Weather Service radar, B
so here's
is
an
about
example of a National Weather
14,255.
Service
WSR-88D image. So this is a plan position indicator. So this is not a constant altitude. So as you move further and further away from the radar itself, the beam is getting higher and higher in the atmosphere. This happens to be a 0.5 degree elevation angle. And then over on the right, we have the color scale, which is referred to as the dBZs, or the decibel scale of the reflectivity factor Z. And of course, the reds on this one have a very large return signal, which means that since the reflectivity factor is a function of diameter to the 6th power, then this is an indicator of large droplets, and large droplets are an indicator of large rainfall rates. And then, of course, it goes from the reds to the oranges to the yellows to the greens and to the blues. Blues are 15 and dBZs and below. And most of the time, the blue on the radar, the droplets are small enough to where they'll evaporate before they reach the ground. The green will often be light precipitation reaching the ground. Yellow will be moderate. And then we get to the red, and that's heavy precipitation. So we have these empirical relationships between the reflectivity factor Z and the rainfall rate. Unfortunately, what we've determined is that there's not one equation that we can use that will accurately describe the relationship between the rainfall rate and the reflectivity factor for all different types of storms. And so if we have stratiform precipitation, we essentially have they all take the form of Z is equal to a constant times the rainfall rate to an exponent. But the constant out front and the exponent are different depending upon the type of precipitation that we're getting, which presumably affects the raindrop size distribution. And that raindrop size distribution will have a big impact upon the rainfall rate. So we typically have really large droplets in tropical convective systems and summer deep convection, and there we will have smaller exponents on the rainfall rate. So the general stratiform precip is going to be 200 times the rainfall rate to the 1.6, and winter stratiform precip in the eastern half of the United States will be 130 times the rainfall rate raised to the 2 power, and so forth and so forth. So if we have our radar return signal strength, and we pick one of those rainfall reflectivity relationships, then we can estimate the amount of rainfall that we're getting for a given dBZ. So the standard one that's used by the National Weather Service is presented here. And so when we have a dBZ of 30, then that translates to an estimated rainfall rate of 0.1 inches per hour. And that assumes that the droplet size distribution matches what we're using in the algorithm to convert the reflectivity factor to a rainfall rate. And there's a lot of uncertainty that goes into that. So what you're going to find is that the rainfall estimates from radar have a lot of error and uncertainty in them relative to ground-based observations. So if you get up to a rainfall rate of, an inch an hour, which is a pretty significant rainfall rate, that would be a dBZ of 47, which would be in the orange. And by the time you get up to a rainfall rate of 4 inches an hour, we're talking DBZ values of 55, which would be red. And if you have supermassive, incredible rainfall rates, in excess of 8 inches an hour, then you're talking about starting to move into a deep red color on the radar display. And the purples, 65, 70, 75, and whites above 75 are usually associated with hail formation in these clouds, and typically speaking, large hail would provide the DBZ values that are up in the 65 to 75 plus range. So how does the radar echo intensity in DBZs, how do we actually describe that in terms of the rainfall rate? So once again, this is using one of the standard algorithms for the National Weather Service. So DBZs up to 30 would be classified as moderate as light precipitation. Between 30 and 40 DBZs would be moderate. Between 40 and 50 DBZs would be classified as heavy precipitation, and anything greater than 50 would be listed as extreme. When we start getting DBZ values greater than 55, we might have hail, and by the time we get to giant hail, we're looking at DBZ values greater than 65. And you can see the corresponding rainfall rates using one of the National Weather Service algorithms as well. There are different types of radar that utilize different wavelengths, and by utilizing different wavelengths, you can actually make the reflectivity target factor match the size of the target that you are actually interested in. So the radar band, which we refer to as L, which is the longest of the radar bands, uses a wavelength of 15 to 30 centimeters, which is all of these are going to be in the microwave. And these are basically going to be transparent to small targets, and can be used to identify aircraft, is primarily what they're used for. The S-band, which is the normal National Weather Service WSR-88D, is using wavelengths between 7.5 and 15 centimeters. And these radar beams are sensitive to precipitation. They can be sensitive to particles in the atmosphere if they're large particles and near the radar. They can also pick up insects and birds. You'll often see insect swarms and bird migrations on the National Weather Service radar as well. The C-band between 3.75 and 7.5 can also be used for the same types of things, the precipitation, the particles, and the insects. The X-band is a shorter wavelength. It interacts better with cloud droplets and ice crystals, and so it can also see precipitation, but it's the first of the radar beams that can actually see information about what's going on inside the cloud. But most of the time, when you're dealing with inside the cloud, we're dealing with the KU and the KA bands, which will be able to identify, cloud droplets, ice crystals, and small particles. And these KU and the KA are often used from mobile platforms, and like Doppler on wheels can use those sorts of things to understand what's going on in the atmosphere associated with individual clouds. Some radars can only measure the DBZ values, which will give you information about the precipitation in the cloud. Other radars that are a little more sophisticated can make use of the Doppler effect to get additional information out of the atmosphere. And the Doppler effect is just based on frequency changes associated with moving objects. So if we have an electromagnetic energy that's scattered by these hydrometeors that are moving either toward the radar or away from the radar, actually cause a frequency change in the transmitted pulse. And by measuring that frequency change of the return signal, we can actually get some information about the radial velocity of the hydrometeors either toward the radar or away from the radar. So here, we're all familiar with the Doppler effect, you just don't know it. So for example, if you are observer number 2 and this car is traveling to the right and it's traveling towards you, and you'll hear a higher pitched sound. You know, let's say the car was honking its horn as it was driving. You would actually hear a higher pitched sound because the wavelength of that horn is going to be a shorter wavelength because of the motion of the car, which means that the frequency is going to be higher, which means it's going to be a higher pitch. And consequently, observer number 1 behind the car, the sound wave is going to have a longer wavelength, which means a lower frequency, which means a lower sound from that observer. And the difference in the pitch heard by observer number 1 and observer number 2 is directly related to the speed of the vehicle. The faster the vehicle is moving, the larger the frequency shift is going to be from the horn on the car. The same thing is happening in the atmosphere. We have our transmitter-receiver system from our radar, and it's bouncing that beam off of targets that are in the cloud. If those objects are moving toward the antenna, then it's going to increase the frequency, and if those objects are moving away from the transmitter, then they will decrease the frequency. And when we plot up on a planned position indicator, we can see broad-scale patterns associated with the Doppler effect. So in this case, the Doppler radar is off to the upper left part of this, and the reds are indicating flow away from the radar, and the greens are looking at flow towards the radar. So at this one position out here, you actually have air that is green touching red, and we have, what that means is that we have rotation in the atmosphere. So we have an area where we have outflow right next to a region of inflow, and that's going to be creating a rotation that we refer to as the mesocyclone of a cumulonimbus cloud. So let's take a look at what a Doppler wind profile would look like for a situation where we have a constant wind from the west to the east. So recall that the Doppler radar can only see the winds that are in the radial direction, either toward or away from the radar. And in this particular example, we have the warm colors, the reds and the oranges, which are defined as wind that is away from the radar, and the cool colors, the blues, are winds that are toward the radar. So if we look right along the east-west axis, that is where the radial wind will be the strongest. So from the west, we'll have the strongest winds directly towards the radar at that location. And then in the east, we'll have the strongest winds away from the radar at that location. If you look north and south of the radar, the winds that are directly north and south of the radar have no radial component either toward or away from the radar, and would therefore register a radial velocity of 0. Let's look at a slightly more complicated scenario here, where we have winds that are no longer constant. These are all in the same direction, but the wind speeds are changing with height. So for example, in the western direction, we have winds that are increasing in strength with height up until about 6 kilometers, and then decreasing in strength with height above that. And so when we look off into the west, these winds, of course, are going to be strongest, moving with a radial velocity towards the radar, immediately along the western azimuth angle, if you want to think of it that way. But because the radar beam has an elevation angle, it's also slicing through the atmosphere at an increasing altitude as you move further away from the radar. So initially, the wind speeds are going to get stronger, and then as you move above that level, as you get further away from the radar, then the winds are going to get weaker again, and that shows up in the Doppler profile on the western side of the Doppler radar. On the eastern side, we have winds that increase in height, increase in speed with height continuously from low level to high level. And once again, because these are winds that are not changing directions, then we're going to have the strongest wind component directly along the azimuth for the east wind, or for the westerly wind that's moving off toward the east. But as you move up higher in the atmosphere, as you get further away from the radar because of the elevation angle of the beam, the winds are going to get stronger. So you can actually see that in the Doppler radar display. Now we're getting more complicated. So now we have a situation where the wind is backing with height. So it's from the south at low levels, and then we'll alternate and basically switch to the west at a higher elevation. And the wind speed here is the same strength at all of those elevations as well. And we'll see what the corresponding Doppler image looks like. So if you look immediately at the south, we have close into the radar at the south, we have the strongest wind, the strongest radial component in the north-south direction. It's moving from the south to the north. And then, by the time you get to a higher elevation, we'll get stronger winds that are at a stronger radial component of the winds that are further away from the radar, then that corresponds to a higher elevation. And by the time you get to the highest elevation, in this case furthest away from the radar, the strongest radial components of the winds are in the east and the west direction. And you'll see that the interpretation of the Doppler radars can be quite challenging. In this situation, we don't have any speed shear, we only have directional wind shear. But in the atmosphere, most of the time, you have both speed shear and directional shear, which makes it more difficult to interpret the Doppler radar displays. So here we have an idealized situation where we have a wind reversal below 6 kilometers. Below 6 kilometers, we have very strong winds that are decreasing in intensity and magnitude until you reach 6 kilometers. And then it basically switches over to a westerly component and then gets stronger with height and then weaker with height. So this is a quite complicated scenario, not very realistic, but we'll look at what the corresponding Doppler radar display would be. So if we look at relatively close to the radar, which corresponds to lower elevations, we have winds from the west to, or excuse me, from the east to the west. And you can see that in the Doppler display with the blue colors to the east and the red colors to the west. And the strongest winds are about 3 kilometers up. So the winds are getting stronger with height and then getting weaker with height. And you can see that in the displays for the Doppler as well. And then as you move above 6 kilometers, that corresponds to a certain distance away from the radar display. The winds have reversed, and we're now into a westerly wind, so wind coming from the west. And you can see that on the Doppler display, with the strongest radial winds being located along that east-west transect, far from the radar. And both of those essentially have a maximum in the wind before you get to the maximum range of the radar. So there's a elevation range where you have the maximum radial winds, and then the winds start to decrease after that. So quite complicated, but yet the Doppler display can be interpreted to give you your wind profile. But if you actually want to get a straight up wind profile, one of the things that we can use obviously is a Raywin sonde. We can launch our balloon and we can measure the wind speed and direction at different altitudes. That is kind of like the gold standard for what we do with how the winds change with height. And these wind profiles are measured with the Raywin sonde, but the problem is that we only launch the Raywin sondes twice a day. So we only get information about the vertical variation in the wind speed and direction twice a day. And in addition, these wind profiles are only collected at locations where we have Raywin sondes, which are not very dense network as well because of the expense associated with that. So one of the things that we can do to augment the wind profiles is to use the Doppler effect and a system that is dedicated to getting information only about the wind speed and direction with height, and we refer to that as a wind profiler. So here we have a wind profiler in Purcell, Oklahoma, and it's using the Doppler effect to determine the wind speed and direction from half a kilometer all the way up to 16.5 kilometers above the ground. It's using the Doppler effect, and it's bouncing its radiation waves off of particles in the atmosphere, so that this particular wind profiler does not require clouds, it does not require precipitation, and it can basically produce a vertical wind profile every 6 minutes. And we can then use those to generate hourly profiles, which have a much higher resolution than our Raywin sondes. So where are we primarily having these NOAA wind profiling network? It's primarily in Tornado Alley, in Texas, Oklahoma, Kansas, and the surrounding states. Why is that the case? Because the wind profile, as we've learned before, the wind shear is really important to predicting severe thunderstorms and the potential for tornadoes. So the National Oceanic and Atmospheric Administration has built these wind profiling networks to give us more dense information about wind shear in the atmosphere to help us better predict the formation of severe thunderstorms in that region. So here's an example of data from the Hillsborough, Kansas wind profiler. And the way this data is typically presented, we have a time axis on the x-axis and a vertical axis is height. So on this particular one, we have data from January 24th of 2011. On the right, we have the data from 7 UTC, and then on the left we have the data at 18 UTC. So what we're looking at is the most recent data, the most recent sounding is the one on the left, and the oldest is the one on the right. So what we're looking at is we're looking at the time variation of the wind profile as determined by this wind profiler in the air above Hillsborough, Kansas on this particular day and time. So if we look at the initial time way over on the right, the wind is primarily from the west, even at low levels, and it gets stronger with height, and we have a maximum wind speed up around 200 millibars, so 20 kilopascals. And the units on this wind profiler are not in knots, but they're in meters per second. And so we have the dark green up there, which gives us winds around 30 meters per second. If we move to the left and we'll look at a single altitude, so let's start off at the surface. The winds are from the west, and then it gets stronger from 10 meters per second to 15 meters per second. And then they get a little bit weaker to 5 meters per second, but then they change direction. They change from the west to from the north, and then they get back to 10 meters per second. So we had a wind shift at the surface, and that wind shift initially occurred only at the surface, but then as time progressed, that wind shift started to affect a little bit higher and higher elevations until it has basically impacted the lower 3 kilometers or 4 kilometers of the atmosphere. And this actually corresponds to the passage of a low-level cold front. So we had winds from the west, and they changed to winds from the north, and it was a layer of cold air that was about 3 to 4 kilometers deep that passed over this site. And at the same time that this cold front was passing over the site, the winds, they're actually developing stronger winds above the site. So at the initial time period over on the right, the strongest winds were 30 meters per second and were located at about 20 kilopascals. By the time of the most recent observation, the peak wind speed is up around 45 meters per second, and the elevation of that wind speed max has decreased from 20 kilopascals down to closer to 30 kilopascals, or from about 12 kilometers down to about 9.5 kilometers. So you can see that there's a wealth of information in here, but it's primarily giving you information about how the atmospheric conditions are changing. And that can be really useful in helping to predict the shear environment for thunderstorms, but it can also be used to look at the outflow from thunderstorms or the structure of a cold front that has moved through the area as well. Lots of information can be gleaned from the single wind profiler from the single location. So, as just mentioned there, they provide almost real-time data every 6 minutes instead of twice a day. They can identify the passage of upper level and surface fronts. They can identify boundaries from large supercell thunderstorms, and they ultimately just help us to improve our weather forecasts.